Hello everybody. Today we will discuss the Faraday's law. You know that from the experiments of Faraday's, when a flux of magnetic field through some loops is changing, then in the loop will occur the EMF, E equal to minus d phi of B over dt. E is the electromotive force, and when in the loop we have the resistance of R, then you will have the induced current IC is E over R. I will show you how we can explain this minus sign in the formula here. To understand this minus sign, you have to use the Lenz's law. It states that when, for example, d phi here is positive, then the electromotive force will be negative and vice versa. So, for example, I prepare here a loop for you to practice that. Imagine that we have the loop here or the loop here. The loop is put in a magnetic field of B, right? This is vertical. Now, when the phi of this magnetic field through this loop is, let's say, increasing, or here another one, phi B is decreasing, then what is the direction of this induced current in the two loops here? For the first one, you will know that when B here is bigger, then the phi B is increasing. So with the minus sign here, the induced current will be created in the loop so that it will create another magnetic field that is opposed with the original one. So this is called, let's say, B prime. Then we use our right hand rule to determine the direction of this current. You put your right hand rule this way, but your thumb will follow the direction of the B prime. Then you will easily see that the direction of the IC will be this way. Correctly? Okay, this side is in front of you. For this case, the current will create another B. This is B prime. Then when you use your right hand with your thumbs up, you will find that the IC has this direction. Okay? So this is how we implement this minus sign in the real situation. Now I would like to talk about the Maxwell Ampere's law. You will see that from the Ampere's law, you have the line integral of B ds is equal to mu 0 multiplied with the current. But for the changing or varying electric field, Maxwell expand this normal current with another one. He called that is the displacement current. So we get the new equation like the integral of B ds here will be the normal current plus the term for the displacement current. This is d phi e over dt. You will see here in this term we have the flux of the electric field through some area, and when we don't have the normal current here, the current by the motion of charge like free electron in the conductor. When we don't have that, then when we have the changing electric field, we also have the magnetic field. So in other words, we can say that when we have the changing electric field, we have magnetic field. So when you compare this derivative with this derivative, you will see the similarity between the two, right? But the difference here is this side. We have here the plus side, here will be the minus side. So how can we implement that in, for example, in the previous example here? So let's say now I have the line, the closed line, in which I will calculate this integral. Then the existing electric field is here. Another one, I take another loop with the electric field. Then in this case, the flux of this electric field is increasing, and for this one, the flux is decreasing. So what happened with the magnetic field created by the changing electric field in the two cases? First of all, when the phi is increasing, then the current has the same direction with the existing E. So I draw the current, we call it the displacement current, ID. Then, similar to the magnetic field created by some current, we use our right hand rule and we will determine the magnetic field created by the increasing electric field. Or for example, at this point, you will have the B, like this one. Okay, for this one, because phi E is decreasing, so the displacement current is downwards, then we can use our right hand rule to determine the magnetic field. So in this case, you will have the magnetic field at this point is outward, and at this point is into the ball.